Catastrophic forgetting is a problem that affects modern machine learning systems, in which a system trained on a sequence of tasks suffers performance losses on older tasks as it learns to perform newer ones. In this work, performed by Ethan Dyer, Maithra Raghu, and myself, we conducted experiments aimed at understanding two aspects of how catastrophic forgetting manifests in practice. First, in feed-forward neural networks, does catastrophic forgetting corrupt each layer's representations of the dataset equally, or is there some variation across layers? Second, how does the degree of semantic similarity between tasks affect the amount of forgetting a network will incur? We explore these questions in the context of image classification with two different setups. First, in the standard split CFAR10 setup, we divide the CFAR10 classes into subsets, and each task consists of classifying between labels in one of the subsets. Here, the identity of the task is known to the network during training and inference, so we use a multi-head network with separate readout layers for each task. The second setup, using the CFAR100 dataset, is designed to mimic input distribution shift. Here, each task consists of classifying between CFAR100 superclasses, like people or vehicles. But when we switch tasks, the subclass corresponding to each superclass is changed. For example, the vehicles images switch from being bicycles to buses, for example. Here, we use a single head setup, as the task identity is not known by the network. To ensure that our conclusions are general, we studied three different image classification architectures: VGG, ResNet, and DenseNet. As the slide shows in the case for the split CFAR10 setup, all three of these models exhibit significant forgetting when trained on two different 5-class splits of CFAR10 in sequence. We use a set of different experiments to study how this forgetting affects internal network representations. First, we use CKA, or Centered Kernel Alignment, to compute similarity scores between network representations of the original dataset before and after forgetting occurs. We find across many different splits and network configurations and in both the datasets that representations deepest in the network are the ones which change the most throughout forgetting. Representations closer to the input change comparatively quite little. Other experiments we performed pointed at the same conclusion. For example, we can reset layers to their pre-forgetting values, finding that when we reset the deepest layers, we can recover a decent amount of performance. We can also retrain certain layers on the initial task, keeping the rest of the network frozen. And again, all of these experiments point at the conclusion that forgetting is not distributed evenly across network representations, but is primarily affecting the deeper representations. Next, we looked at how semantic similarity between tasks in a sequence affected the amount of forgetting. We wanted to know whether, in general, task sequences with semantically more similar subtasks resulted in more or less forgetting than task sequences with semantically less similar subtasks. And initially, we find somewhat conflicting results. For example, when we train a network initially to classify between two vehicles, and then train it on a next task involving either vehicles or animals, we found that when the tasks were similar, that is, both vehicles, the network forgot less. However, in a slightly different setting, where the initial task consisted of both vehicles and animals, and the second task consisted of just vehicles, here the network's ability to recognize vehicles suffered more than its ability to recognize animals. So here, semantic similarity appeared to increase the amount of forgetting. Now, these two results seem to be in tension, which led us to develop a simple toy model to try and understand what was occurring in both cases. This toy model was inspired by earlier observations that shallow features don't change as much, and so it treats the features as frozen after training on task 1 with just the final layer parameters of the model changing. Now, an analysis of this model shows two phenomena. First, when tasks in a sequence lead to model representations which are nearly orthogonal, then training on the second task doesn't have much of an effect on the original task representations, and there is minimal forgetting. At the other extreme, when the representations of each task lie in the same subspace or are nearly parallel, then as long as the labels are similar, there will also be minimal forgetting. So this model suggests that forgetting will be maximal for task sequences with an intermediate degree of semantic similarity. And to test this prediction in real networks, we ran an experiment in which we tuned, using mix-up, the degree of similarity between subsequent tasks. And as expected from the frozen feature model, we do in fact see that the network forgets the most when subsequent tasks are neither very similar nor very dissimilar. So, to conclude, in this work, we've studied two different aspects of catastrophic forgetting, one related to layer wise representations, and the other related to semantic similarity, and we hope that this will lead to a deeper understanding of this phenomenon. Thank you.